Okay, welcome to the lecture 2. Before starting this lecture, let me tell you about some definition. Definition number 1, which is curve. Curve is basically the aggregation of all points in n-dimensional space and which satisfy the n-parametric equation is defined as aggregate of points in n-dimensional space, and it satisfies n-parametric equation. And these equations are like this: x to the power I dx to the power I t, where I is from 1 to n. Okay, next definition is of subspace. Subspace is of say dimension m dimension of space of dimension is aggregate of points which satisfies m-parametric equation, and these equations are x, the I is x to the power I, t1 t2 up to the power up to t to the n, up t to n, tn, and n is, sorry, here is m. Okay, and m is less than n. Okay, where t1 t2 up to tm are m parameters. If in this condition case, say m equals to n minus 1, then that type of subspace we will call hypersurface. Subspace is called hypersurface. Now the coordinates of a point in three-dimensional rectangular space are given by x, y, z if I'm talking about Cartesian coordinate. Okay, but what if someone asks us that how can you define a point in n-dimensional space? Then we can't say that it is x, y, z, p, q. Then maybe after 46 letters our a, b, c, d will be fully vanish. Then the easy way to do this is to use x to the 1, x to the 2, x to the 3, and up to the x to the n. These are not the powers. Okay, these are simply just the superscripts. And that's how we will define the coordinates in n-dimensional space. Okay, now our next topic is transformation of coordinate. Transformation of coordinates. Okay, as we all know that in plane geometry, to specify any point we just need two Cartesian coordinates, which are x and y, and in polar coordinates we need just only two components, which are r and theta, as all these points contribute together to form a plane, and that is said to be two-dimensional manifolds. All this point of two-dimensional, all this point in two-dimensional constitute to form plane. Are said to form two-dimensional manifold of points. So that is a number of dimension of manifold tells us the number of independent coordinates required to specify a point on it. Same for the three-dimensional coordinate in Cartesian coordinate, which is x, y, z, and all these points in three-dimensional constitute to form a three-dimensional space, are said to form three-dimensional manifolds. And the dimension of these manifolds tell us the coordinates required to specify a point on it. Same for the n-dimensional x1, x2 up to x2n. All these points in n-dimensional constitute to form a n-dimensional space, are said to n-dimensional manifolds of point, n-dimensional manifolds of points. Okay, and the number of dimension of this manifold tell us the number of coordinates required to specify a point in that space. So as I told you in introduction, that the work of tensor is to investigate that how the changes take place in a quantities when it transforms from one coordinate system to another coordinate system. To understand this more, let's consider a variable. Consider two sets of variables, x1, x2, x to the n, and x dash 1, x dash 2, x dash 3, and x dash 1. Which are both in n-dimensional space but in two different frames. They are in two different frames of reference. Okay, and these two set of variables are related by the equation x dash I f x1 x2 and xn, and this f of I is single valued and continuously differentiable function, continuous differentiable. Okay. Let me rewrite that equation again, which relates the two different frames x dash I f of I x1 x2 to x2, and these this function f of I is single valued and continuous differentiable. Now if I differentiate this x dash I with respect to xi, then what will I get? Let me write one of that x dash 1 for I equals to 1. and it will be equals to f of 1 x1 x2 to x to the n. Differentiating x dash 1 with respect to x of I. X dash 1 equals to curl x dash dx dash 1 curl x dash 1 or curl x 1 over dx 1 plus curl x dash 1 over curl x2 dx2 and so on for higher number curl x dash 1 over curl x n dx. Similarly, for I equals to 2, x dash 2 equals to f of 1, f of 2, x1, x2 to xn. Okay. Differentiating this with respect to x of I, x dash 2 curl of x dash 2 over x1 dx 1 plus curl x dash 2 dx 2 and so on x dash 2 and dx. Okay, this is 2, sorry. Okay, and similarly, if I'm talk about I equals to n, x dash n equals to f of n, x1, x2 up to x to the n. Then dx, the total differential, dash n equals to curl x dash n over curl x1 dx1 plus curl x dash n over curl x2 dx2 curl x dash n over n dx. Okay, now if I want to write this whole thing in a single form, then how can I write this? This will be look like dx dash I summation j 1 to n curl x dash I curl x dash j and dx j, where j is from 1 to n. Now you can get any of the form that we have listed above. Okay, and according to the Einstein summation convention, which is, he just said that you can drop this summation because we know that summation goes from 1 to n, so we can simply write this as also curl x dash I curl x j dx j Einstein summation convention, which is simply just to drop the summation. Okay, and the matrix of this all coefficients, which all can be written as like this: x dash I over curl x j equals to this one, curl x dash 1 curl x 2 up to curl x dash 1 curl x n curl x to curl x 1 curl x dash 2 curl x 2 this one and last one is this one curl x dash 2 and curl x, and in the end curl x dash and curl x dash curl x dash and curl x 2 up to curl x dash and or curl x. And the determinant of this matrix, let's say J with the determinant of this matrix, okay, curl x dash I over curl x J. The determinant of this matrix is called Jacobian of transformation. Jacobian of transformation. Okay. Thank you.